Right now, drifting through a region of space no human eye has ever seen, and no instrument other than its own has ever directly sampled, a spacecraft the size of a small car is tumbling slowly through the dark. Voyager 1 crossed the final boundary of our Sun's protection on August 25, 2012, and what its instruments registered on the other side has quietly rewritten what scientists understand about the environment that fills the overwhelming majority of our galaxy. The cosmic ray count surged by a factor that eliminated any remaining uncertainty. The magnetic field shifted direction, rotating away from its solar orientation into something older and more alien. The solar wind that had accompanied the spacecraft for 35 years dropped to zero. Not weakened, not faded. Zero. What Voyager found beyond that boundary was not the peaceful emptiness that most people picture when they imagine the space between stars. It was not the serene void of science fiction backdrops and romanticized astronomical illustrations. It was something else entirely. It was a medium that has been pressing against our heliosphere from all directions since before the first human being drew breath. Patient with a patience that has nothing to do with patience because it has nothing to do with time, in any way we experience it. What lies beyond our Sun's protection is not emptiness, it is exposure, and the data Voyager returned, particle count by particle count, magnetic field measurement by magnetic field measurement, plasma oscillation by plasma oscillation, describes that exposure more precisely and more completely than any model or telescope had ever managed before. If these journeys into the deepest verified truths about our universe are what you come here for, hit that like button and subscribe. It means more than you know, and it helps bring more stories like this one to life. Now, get yourself comfortable, let us begin. There is a machine out there right now that almost no one thinks about on any given day, moving at a speed that would cross the continental United States in slightly less than 8 minutes, heading in a direction that will not bring it close to another star system for roughly 40,000 years. It weighs approximately 721 kilograms, which is about the combined weight of a large motorcycle and its rider. Its central bus, the main body of the spacecraft, is roughly the size and shape of a 10-sided box that would fit inside a reasonably large garden shed. From that central body, a boom extends outward, carrying magnetometers designed to measure the extraordinarily faint magnetic fields of deep space, without interference from the spacecraft's own magnetic signature. 3 radioisotope thermoelectric generators hang from another set of booms, slowly converting the heat of decaying plutonium-238 into the trickle of electricity that keeps the instruments alive. A parabolic high-gain antenna 12 feet across points perpetually back toward a blue dot that the spacecraft's cameras, themselves powered down since 1990 to conserve electricity, have not photographed in more than 3 decades. Voyager 1 launched on September 5, 1977, from Launch Complex 41 at Cape Canaveral, Florida, propelled by a Titan 3E Centaur rocket on a trajectory calibrated to swing it past Jupiter and Saturn, using their gravity as a slingshot. The engineers and scientists at NASA's Jet Propulsion Laboratory who designed and built it expected it to function for 5 years. It has now been operating for nearly half a century, having long outlasted the teams that designed its major systems, having outlasted several of the scientists who planned its planetary encounters, having outlasted entire divisions of the institution that oversaw its construction. The technology embedded in its computers is, by any modern standard, primitive to the point that the comparison sounds like a joke. The flight data system processes roughly 80,000 bits per second. A standard home internet connection operates at speeds approximately 10,000 times faster. Its memory holds 67 kilobytes. A modern photograph contains roughly 10,000 times more data. The machine is ancient by any modern measure. And yet this machine, built with components and computing power, that were themselves approaching obsolescence by the time the spacecraft launched, has travelled farther from Earth than any object humanity has ever placed in space, and has returned data from a region of the universe that no human instrument had ever directly sampled before. It crossed the termination shock, the inner boundary of the Heliosphere's edge region, in December of 2004 at approximately 94 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. 94 astronomical units is approximately 8.7 billion miles. It traversed the Helios Heath, the thick, turbulent buffer zone between the Sun's domain and the true interstellar medium, for nearly 8 years after that. And then, on a date that most people alive at the time did not notice and that received less public attention than it deserved, it crossed the heliopause. It entered interstellar space. The story of what it found there is not primarily a story about distance. Distance is the straightforward part. The story is about what fills the distance, and what fills the distance is not what most people think. When news organisations around the world announced in September of 2013 that Voyager 1 had left the solar system, they used a phrase that is scientifically imprecise in a way that matters far more than it might appear. The solar system, defined by the gravitational dominance of the Sun, extends enormously farther than any spacecraft has yet travelled. The Oort cloud, the vast theoretical shell of icy bodies loosely bound to the Sun by gravity, is believed to begin at roughly 2,000 astronomical units from the Sun and extend outward to perhaps 100,000 astronomical units. Voyager 1 is currently at approximately 163 astronomical units. It has not yet reached the inner edge of the Oort cloud. It will not arrive there for roughly 300 years. By the definition of gravitational dominance, Voyager is still very much inside the solar system, and will remain so for longer than human civilization has existed in any continuous form. What Voyager actually left is something different. Something that, in the ways that matter most for any object travelling through space, is arguably more significant than any gravitational boundary. Voyager left the heliosphere, and that distinction is not a technicality designed to satisfy pedantic astronomers. It is the entire point of the mission, and understanding it is the only path to understanding why the data Voyager returned is as consequential as it is. The heliosphere is the bubble of charged particles and magnetic fields that the Sun continuously inflates around itself through the constant outward flow of the solar wind. It is the region of space where the Sun's direct physical influence shapes the local environment. Inside it, the magnetic field is solar in origin, carried outward by the solar wind. Inside it, the dominant charged particles are products of solar process, accelerated by solar flares, compressed by the solar wind, modulated by the 11-year solar cycle. Inside it, the radiation environment is set by our star and filtered through the turbulent magnetic structure that our star generates. Outside the heliopause, none of that applies. The magnetic field is galactic in origin, shaped by supernova explosions and the bulk motion of interstellar gas clouds and the currents flowing through plasma that has been in place since long before our solar system formed. The dominant charged particles are galactic cosmic rays arriving from sources scattered throughout the Milky Way. The radiation environment is set not by our star, but by the accumulated violence of the galaxy, operating on timescales that dwarf the entire history of Earth. Voyager crossed from one regime into the other. It is the only human-made object that has ever done so, and the measurements it took in the process amount to the first direct characterization of what galactic space actually contains when you go and measure it, rather than infer it from a distance. To understand what Voyager found, you first have to understand what it left behind. The heliosphere begins with the Sun itself, specifically with the corona, the outermost layer of the solar atmosphere, which presents one of the most persistent unsolved problems in astrophysics. The surface of the Sun, the photosphere, has a temperature of roughly 5,800 Kelvin. The corona, which lies above the surface, somehow reaches temperatures exceeding 1 million Kelvin. This is not a gradual gradient. It is a sharp and physically counterintuitive inversion. Imagine walking away from a campfire and finding that the air 10 feet away is 1,000 times hotter than the flames themselves. That analogy, while imperfect, conveys the correct scale of the paradox. Several mechanisms have been proposed to explain coronal heating. The dissipation of magneto-hydrodynamic waves propagating upward from the solar interior. Magnetic reconnection events at small scales called nanoflares. The precise balance of these contributions remains an active area of research, but the consequence of that heating is settled physics, verified by decades of spacecraft observation. At 1 million Kelvin, the thermal energy of coronal particles exceeds the gravitational binding energy at the Sun's surface. The material cannot be held. It boils continuously away from the corona in a supersonic flow of protons, electrons, and heavier ions, streaming outward in every direction at speeds ranging from roughly 300 to 800 kilometers per second, depending on the conditions at their point of origin. This is the solar wind. It is not occasional, it is not tied to storms or flares or any intermittent solar event. It flows continuously every second of every year and has been flowing for roughly 4.5 billion years. It has never stopped. It will not stop until the sun exhausts its fuel. Carried within this wind, frozen into the plasma by its high electrical conductivity, are the magnetic field lines of the sun itself. As the sun rotates at approximately 1 revolution per 27 days at its equatorial latitudes, these embedded field lines wind into a vast three-dimensional spiral pattern. This pattern was first described mathematically by the physicist Eugene Parker in 1958 in a theoretical paper that was initially rejected by reviewers who found its predictions too radical to credit. Parker predicted the solar wind before any spacecraft had measured it, and he was correct in every important detail. The structure he predicted, now called the Parker spiral, extends outward through the entire solar system. It threads the space between every planet, every asteroid, every comet, every grain of interplanetary dust. It is the skeleton of the heliosphere, the magnetic framework upon which the sun's protective bubble is constructed. This wind and its embedded field flow outward past Earth at roughly 400 kilometers per second, past Jupiter in about 2 weeks, past Neptune in about 4 months, past the Kuiper belt, past the scattered disk of distant icy bodies, thinning as it expands across an ever larger volume but never stopping, until it meets something capable of stopping it. That something is the interstellar medium. The interstellar medium is not empty space. It contains a thin but measurable population of gas and dust and magnetic field that pervades the space between every star and every other star in the galaxy. This medium exerts pressure, not pressure that a human being could feel, not pressure that any instrument sensitive to atmospheric conditions could detect directly, but in the physics of large-scale plasma dynamics, where relative pressures are measured in trillionths of a Pascal, and where equilibria are established over distances spanning astronomical units, the pressure of the interstellar medium is substantial enough to define a boundary. Where the outward push of the solar wind equals the inward push of the interstellar medium, the heliopause forms. Inside the heliopause, the sun controls the environment. Outside it, the galaxy does. Voyager 1 crossed from one side of that boundary to the other. It is the only instrument that has ever been on both sides. The transition did not happen abruptly. It occurred in stages, each one revealing something about the structure of the heliosphere that decades of remote observation and theoretical modelling had only approximated. The first stage was the termination shock, which Voyager 1 crossed in December of 2004 at approximately 94 astronomical units from the Sun. Voyager 2, following a different trajectory toward the southern hemisphere of the heliosphere, crossed the termination shock in August of 2007 at a closer distance of approximately 84 astronomical units. The 10 astronomical unit difference in crossing distance between the two spacecraft was itself a significant finding. It demonstrated that the heliosphere is not a sphere. The solar system is moving through the local interstellar medium at roughly 26 kilometers per second relative to the surrounding cloud of interstellar gas, and this motion compresses the heliopause on the leading side while allowing it to extend somewhat farther on the trailing side. The asymmetry in termination shock distances between Voyager 1 and Voyager 2 confirmed this prediction with direct measurement. The termination shock itself is the region where the supersonic solar wind is forced to abruptly decelerate to subsonic speeds. The solar wind has been travelling outward faster than the speed at which pressure disturbances can propagate through the medium. At the termination shock, it begins to feel the back pressure of the interstellar medium for the first time. The transition is violent in terms of the physics involved. The kinetic energy of the decelerating wind converts into thermal energy in the post-shock region. Temperatures in the heliosheath, the zone immediately beyond the termination shock, can exceed 100,000 Kelvin. The solar wind does not stop at the termination shock. It slows, compresses, and heats, then continues moving outward in a denser, hotter, and far more turbulent form into the heliosheath beyond. Both Voyager spacecraft spent years crossing the heliosheath, and the measurements they took in that region were significantly stranger than most pre-mission models had predicted. The magnetic field in the heliosheath was chaotic. Field lines folded back on themselves in ways that violated the smooth spiral geometry of the inner heliosphere. Magnetic bubbles formed spontaneously in the turbulent post-shock plasma. They trapped energetic particles, releasing them unpredictably as the bubbles expanded and contracted. The heliosheath proved to be not a calm buffer zone, but a region of active physical conflict between two great fluid systems pressing against each other, each imposing its own magnetic character on the plasma at the boundary between its domain and its neighbours. It was, in every measurable sense, a contested zone. Then, after years of crossing it, both spacecraft registered the final transition, and the measurements that accompanied it changed the terms of every subsequent conversation about what the galaxy looks like from inside. The detection of Voyager 1's heliopause crossing required patience, sophisticated analysis, and ultimately an unexpected source of confirming evidence. In June and July of 2012, the spacecraft's cosmic ray subsystem and its low-energy charged particle instrument began registering dramatic changes in the particle population surrounding the spacecraft. The flux of anomalous cosmic rays, a category of particles that are a product of the heliosphere's own internal physics, and that can exist only inside the heliopause, dropped precipitously over a period of just a few days. This drop was not gradual, it was a cliff. 1 week, the anomalous cosmic rays were present at their established heliosheath levels. The next week they were gone. Simultaneously, the flux of galactic cosmic rays, particles originating from sources distributed throughout the Milky Way, surged upward sharply. The particle data pointed unmistakably toward a heliopause crossing, but the magnetic field data initially complicated the interpretation. Scientists had expected that crossing the heliopause would produce a sharp, clear rotation in the direction of the magnetic field, a pivot from the solar field orientation to the interstellar field orientation. Instead, the field rotated gradually over days to weeks. Some researchers argued that this gradual rotation meant Voyager had entered an unexpected transition region, neither fully inside the heliosphere nor fully in interstellar space. Others maintained that the spacecraft had genuinely crossed the heliopause, and that the boundary was simply more complex and more gradual than the clean spherical shell that theoretical illustrations typically depicted. The debate played out in the scientific literature and at conferences throughout 2012 and into 2013, with neither camp able to conclusively resolve the question using the available data. The resolution came from an event that had nothing to do with Voyager's instruments directly. In March of 2012, a powerful coronal mass ejection erupted from the Sun. This massive burst of solar plasma and magnetic field accelerated outward through the heliosphere at more than 1,000 kilometers per second. When the shockwave from this eruption finally reached Voyager 1's location, more than 120 astronomical units from the Sun, and many months after the initial eruption, it caused the surrounding plasma to oscillate at frequencies determined directly by the local electron density. Voyager 1's plasma wave science instrument detected these oscillations. The frequency it measured corresponded to an electron density of approximately 0.08 electrons per cubic centimetre. In the outer Helios heath, the solar wind plasma density had been roughly 0.002 electrons per cubic centimetre. The measured value was approximately 40 times higher, not slightly higher, not marginally elevated, 40 times denser than anything the Helios heath had produced at that location. There was only one region in the known structure of the solar environment where plasma at that density existed, the interstellar medium. The measurement was decisive. Working backward through the particle data, the magnetic field records, and the plasma wave measurements, scientists at JPL and collaborating institutions pinpointed the crossing. Voyager 1 had passed through the heliopause on or around August 25, 2012, at a distance of approximately 121.7 astronomical units from the Sun. The announcement came in September of 2013. For 13 months before that announcement, without anyone on Earth being certain of what had happened, Voyager 1 had been immersed in interstellar space, collecting data that no instrument had ever collected before, measuring particles and fields and plasma in an environment that every previous observation had been forced to study from the inside, looking outward through the distorting lens of the heliosphere itself. Not inferred, not modelled, not calculated from the absorption spectra of distant starlight, measured directly by instruments pressed against the actual material of the interstellar medium, reporting what they found at 160 bits per second across 15 billion miles of dark. Voyager 2's crossing in November of 2018 expanded the discovery in ways that gave scientists something Voyager 1's crossing alone could not provide. On November 5, 2018, at a distance of approximately 119 astronomical units from the Sun, Voyager 2 crossed the heliopause. The crossing point, 3 astronomical units closer to the Sun than Voyager 1's, confirmed the heliosphere's asymmetry with direct measurement from a second independent instrument. But the more significant contribution came from an instrument that Voyager 1 had lost 42 years before its heliopause crossing. Voyager 2 still carries a functioning plasma science instrument, designated the PLS, which can measure directly the speed, density, temperature, and flow direction of charged particles in the surrounding medium. Voyager 1's equivalent instrument failed in 1980, before the spacecraft had even reached Saturn, let alone the heliopause. Everything Voyager 1 could tell us about the plasma of the interstellar medium came from indirect inference through plasma wave oscillation frequencies. Voyager 2 could measure the plasma itself. The PLS data from the crossing was unambiguous and immediate. At the heliopause boundary, the outward flowing solar wind plasma disappeared abruptly. One moment Voyager 2 was immersed in the decelerating but still flowing solar material of the inner Helios heath, moving at roughly 100 to 150 kilometers per second relative to the Sun. The instrument registered the flow clearly. The next, that flow had ceased entirely. The solar wind speed dropped to 0. In its place, the instrument detected a plasma population that was denser by a factor of roughly 25 to 30, warmer in terms of particle kinetic energy, and essentially stationary relative to the spacecraft. This was the interstellar plasma, material of galactic origin that had never been directly measured by any human instrument. The transition was sharp in a way that Voyager 1's crossing had not fully demonstrated. It was not a gradual blending of solar and interstellar material. It was a boundary, and crossing it produced a step change in every plasma property the instrument could measure. 2 spacecraft, 2 independent crossings 6 years apart in different directions through different parts of the heliosphere's surface. 2 complete sets of instruments registering the same fundamental transition from different angles and at different times. The scientific case was not merely strong, it was conclusive in the way that the best science becomes conclusive, through independent repetition that confirms rather than merely extends. Start with the particles, because the particles are where the crossing is most legible and where its implications are most immediate. Voyager 1 carries 2 instruments capable of detecting energetic charged particles: the cosmic ray subsystem, which measures particles with energies above roughly 1 million electron volts, and the low-energy charged particle instrument, which covers a broader energy range including lower-energy ions and electrons. Together they functioned as a continuous particle census for 35 years of heliospheric travel, cataloguing the charged particles that surrounded the spacecraft at every point along its trajectory from Earth outward. Inside the heliosphere, the particle population was dominated by 2 primary types of energetic charged particles. The first were particles of solar origin, solar energetic particles accelerated by flares and coronal mass ejections to energies of millions of electron volts and flung outward into the heliosphere by the violence of those events, and solar wind ions, the low-energy protons and electrons that constitute the solar wind itself. The second type were anomalous cosmic rays, and they require explanation because they represent one of the most interesting byproducts of the heliosphere's existence. Anomalous cosmic rays begin as neutral atoms from the interstellar medium drifting inward toward the Sun. Because they carry no electric charge, they are not deflected by the heliosphere's magnetic field and pass through the heliopause freely. Once inside the heliosphere, solar ultraviolet radiation ionizes them. It strips away their electrons and transforms them into charged particles. The solar wind's magnetic field then captures them and carries them along. When these newly charged particles eventually reach the termination shock at the heliosphere's inner boundary, they undergo a process called diffusive shock acceleration. They bounce back and forth across the shock front, gaining energy with each crossing, until they have been accelerated to energies far above those of ordinary solar wind particles. Anomalous cosmic rays are, in a precise physical sense, a product manufactured by the heliosphere's own internal physics. They require the termination shock to reach their observed energies. They require the heliosphere's magnetic containment to reach their observed concentrations, and they exist only inside the heliopause. Outside the heliopause there is no termination shock, there is no solar magnetic field, there is nothing to produce them. When Voyager 1 crossed the heliopause, the anomalous cosmic ray population did not gradually diminish over weeks or months as the spacecraft moved progressively deeper into the interstellar medium. It dropped to near zero within days. The acceleration mechanism was behind the spacecraft. The source was gone. The particles that had accompanied Voyager for 35 years simply ceased to exist around it. The particles that had accompanied the spacecraft for 35 years of heliospheric transit simply were not there anymore. Replacing them immediately and completely was the unmoderated population of galactic cosmic rays, arriving at intensities the Saturn craft had never registered in its entire career inside the heliosphere. The galactic cosmic ray flux rose to levels approximately 2 to 3 times higher than the maximum values recorded inside the heliosphere, even during the deepest solar minimum conditions. For lower energy galactic cosmic rays, those below roughly 200 million electron volts per nucleon, the increase was substantially more dramatic. representing a population that the heliosphere had been suppressing by factors of 5 to 10 or more. These lower energy particles are among the most biologically damaging per unit of exposure precisely because they are more readily absorbed by matter, depositing their energy over shorter distances and creating higher ionization densities along their tracks through tissue. The heliosphere's ability to exclude them is one of its most consequential protective functions. Beyond the heliopause, they were simply present, at full galactic flux, arriving from all directions simultaneously without any solar modulation, without any dependence on the solar cycle, without any relationship to anything our Sun does or has ever done. This is what interstellar space delivers to any unshielded object entering it, not during solar storms, not during galactic events, always, continuously, without remission, at every moment of every day for the entire duration of any conceivable transit between stellar systems. Now turn to the magnetic field, because the magnetic field tells the story of the crossing from a different and complementary angle. Voyager 1's magnetometer, mounted on an extended boom to minimize contamination from the spacecraft's own magnetic signature, measures the ambient field strength and direction with sensitivity sufficient to detect fields of a fraction of a nanotesla. To put that sensitivity in context, Earth's surface magnetic field is approximately 50,000 nanotesla. The instrument is measuring fields roughly 100,000 times weaker than that. Inside the heliosphere, throughout 3.5 decades of transit, the magnetometer had been recording the solar magnetic field organized in the Parker spiral geometry. In the outer heliosheath, immediately before the crossing, the field strength measured roughly 0.1 to 0.2 nanotesla. The direction of those field lines was consistent with the expected solar field orientation at that distance and latitude. After the heliopause crossing, two things happened that the magnetic data revealed clearly. First, the field strength increased. The interstellar magnetic field in our local galactic neighborhood, shaped by the currents flowing through galactic plasma and the accumulated effects of supernova shockwaves propagating through the medium over millions of years, has a typical strength in the local area of roughly 0.3 to 0.5 nanotesla. Voyager 1 measured this increase directly. The field went from roughly 0.2 nanotesla inside the outer heliosheath to roughly 0.4 to 0.5 nanotesla outside it. The interstellar magnetic field is actually somewhat stronger than the exhausted and weakened solar field in the outermost region of the heliosphere. This was not universally anticipated. Some theoretical treatments had imagined the region beyond the heliopause as relatively field-free. Not magnetic, not structured, simply present. The reality was different. The interstellar medium is magnetized. Its field is coherent enough to measure over the distances Voyager has travelled through it, stable enough in direction to characterize as a distinct field environment. Second, and more informative for understanding the nature of the boundary itself, the field direction changed. The interstellar magnetic field in our local galactic environment runs at an angle significantly different from the solar equatorial field that organizes the interior of the heliosphere. Voyager's magnetometer tracked this directional rotation, recording a shift in the field vector over days to weeks after the crossing that confirmed the spacecraft had entered a domain governed by galactic rather than solar magnetic processes. The transition was not as sharp as many models had predicted. Theory suggested a near-instantaneous pivot at the heliopause boundary, a clean switch from solar to interstellar orientation that would mark the crossing as precisely as a knife edge. Instead, the rotation occurred gradually, over a period suggesting that the heliopause is a boundary layer of finite physical thickness, perhaps a fraction of an astronomical unit across, where solar and interstellar magnetic fields intermingle rather than simply abutting each other at a geometric surface. The heliopause is not a wall, It is a membrane, permeable in a limited sense, allowing some exchange of material and field between the two great plasma systems it separates, creating a zone of mixed character that neither instrument configuration could fully resolve with the available resolution. This partial permeability had been suspected from theoretical work, but had never been confirmed with in situ measurements until Voyager provided them. And after the crossing, the interstellar magnetic field revealed its own character through the magnetometer's ongoing measurements. Not static, not smooth, but turbulent in ways that reflected the dynamical history of the local interstellar medium. Fluctuations in field strength and direction on timescales of hours to days showed that the interstellar medium is not a calm environment. It is stirred by shockwaves from distant supernova, by the relative motion of interstellar clouds, by the magneto-hydrodynamic instabilities inherent to any electrically conducting fluid threaded by magnetic fields. The medium breathes with a complexity that only direct measurement could have captured. The plasma measurements provided the final piece of the characterization. Voyager 2's functioning plasma science instrument gave scientists the most direct evidence, but both spacecraft contributed to the picture through their respective detection methods. In the interstellar medium, the plasma density measured by Voyager 2's PLS was approximately 0.05 to 0.06 electrons per cubic centimetre. That number needs translation into a form that carries meaning for a human mind. 1 cubic centimetre is roughly the volume of the end of your thumb from the first knuckle to the tip. In that volume of interstellar space you would find, on average, roughly 1/20th of a single electron. In the outer heliosheath, the solar wind plasma density was approximately 0.002 electrons per cubic centimetre, already extraordinarily thin by any terrestrial standard. In the interstellar medium beyond the heliopause, the density was roughly 25 to 30 times higher than that. By any human reference point, both of these densities are so close to zero that the comparison seems meaningless. Earth's atmosphere at sea level contains approximately 25 quintillion particles per cubic centimetre. Even the best laboratory vacuum chambers maintain densities billions of times higher than the interstellar plasma. But the physics that governs plasma behaviour does not care about human reference points. The difference between 0.002 and 0.05 electrons per cubic centimetre is physically significant in a domain where those numbers represent the relevant medium. Denser plasma transmits electromagnetic waves differently. It supports plasma wave modes that lower density plasma cannot sustain. It exerts more pressure on any boundary it presses against. The density jump at the heliopause is the direct physical measurement of the pressure balance that creates the boundary in the first place. The interstellar medium is denser, it presses inward. The solar wind thins and slows. They find equilibrium at the heliopause. Voyager measured both sides of that equilibrium with the precision of a scientific instrument rather than the approximation of a model. The plasma was also warmer in terms of particle kinetic energy than the outer heliosheath plasma. Direct measurements from Voyager 2's PLS place the interstellar plasma temperature at approximately 30,000 to 50,000 Kelvin. This temperature requires interpretation. In plasma physics, temperature refers to the average kinetic energy of particles, not to anything that would feel warm to a human observer. A plasma at 50,000 Kelvin contains particles moving at tens of kilometers per second. But the energy density is so vanishingly small because so few particles are present that you could immerse your hand in this plasma and feel absolutely nothing. The particles strike human skin at a rate so low that the total energy transfer per second would be imperceptible. Temperature without density produces no perceptible sensation. But the temperature is physically meaningful because it reflects the energetic history of the medium. Plasma at 50,000 Kelvin has been heated by something. Ancient shock waves from supernova, turbulent dissipation of magnetic energy, the accumulated thermal history of the local interstellar medium over millions of years of dynamical evolution. And the plasma was stationary, not flowing outward like the solar wind, not moving with any bulk velocity that Voyager's sensors could attribute to local processes, simply present, immobile relative to the spacecraft, filling the space between the stars with the quiet persistence of material that has been there far longer than the solar system has existed. Beyond the particle counts and the field measurements and the density numbers, Voyager 1 detected something that no one had quite anticipated in the form it arrived. It detected a hum, not an acoustic vibration, because the interstellar medium is so thin that mechanical sound waves in the conventional sense cannot propagate through it. What Voyager's plasma wave science instrument detected were electromagnetic oscillations, vibrations in the electric field of the surrounding plasma, a frequency determined directly and uniquely by the local electron density. Higher density produces higher frequency. The relationship is governed by a fundamental equation of plasma physics, and carries the same reliability as any physical constant. The oscillations measured at roughly 2 to 3 kHz. When NASA converted this electromagnetic signal to an audio representation by mapping its frequencies to the range of human hearing, the result was unlike any sound ever captured by a scientific instrument. A thin, sustained tone, almost like the note held on a glass harmonica in a very quiet room, rising and falling slightly as the plasma density fluctuated around its mean value, emerging from a spacecraft 12 billion miles from Earth and received at the Deep Space Network stations as a radio signal weaker than the glow of a birthday candle seen from the distance of the moon. The plasma hum is real. The audio conversion is a translation into human perceptual range, not a metaphor, not a simulation. A direct measurement of electromagnetic oscillation in the surrounding plasma, rendered into frequencies the human ear can detect. The interstellar medium cannot carry acoustic waves of any meaningful intensity, but the underlying electromagnetic oscillation is as physical and as measurable as any phenomenon in space physics, and Voyager was the first human instrument ever to detect it in situ. The hum proved scientifically valuable beyond its arresting quality as a phenomenon. Between the infrequent episodes when coronal mass ejections from the Sun send shockwaves propagating outward through the heliosphere and into the near interstellar medium, the surrounding plasma rings at enhanced amplitude and allows precise density calculations. Between those events, the quiet hum provides a continuous baseline that reveals the ambient state of the medium without requiring any external stimulus. It confirmed that the plasma density remains broadly stable over the years Voyager has been monitoring it, hovering near 0.05 to 0.1 electrons per cubic centimetre, with gentle variations that correspond to small-scale density structures in the local medium. The medium has texture. It is not perfectly homogeneous. Density ripples exist on spatial scales of astronomical units, driven by the same turbulent processes that the magnetometer detected in the magnetic field. The medium breathes slowly and subtly in a rhythm set by forces that have nothing to do with our star and everything to do with the galaxy's own internal dynamics. And the hum encodes that breathing in a signal that arrives at Earth as a continuous record of conditions in a region where no other human measurement has ever been taken. The galactic cosmic rays that Voyager detected arriving at full strength beyond the heliopause are not a single species of radiation. They are a zoo of particles spanning an extraordinary range of energies, masses, origins, and histories. And understanding what they are is essential to understanding why Voyager's measurements carry the weight they do. By particle count, galactic cosmic rays are approximately 90% protons, with helium nuclei accounting for nearly 9%, and heavier ions making up most of the remainder. Carbon, oxygen, nitrogen, silicon, and iron nuclei all appear in the cosmic ray flux, each accelerated to velocities that approach the speed of light by processes operating at scales that dwarf anything in the solar system. The energies of individual galactic cosmic ray particles span more than 12 orders of magnitude. At the low end, cosmic rays carry energies of a few million electron volts per nucleon, comparable to particles produced in medical linear accelerators. At the high end, the most energetic cosmic rays ever detected carry energies exceeding 100 billion electron volts, concentrated in a single subatomic particle. To make that number physically graspable, a proton at that energy carries kinetic energy equivalent to a baseball thrown by a professional pitcher, compressed into a volume smaller than an atomic nucleus. A subatomic particle carrying the energy of a thrown baseball. That is not a loose analogy or an exaggeration. That is the physics. The sources of galactic cosmic rays are the most energetic and violent processes in the Milky Way. Supernova remnants are the primary factory responsible for the bulk of the cosmic ray flux at energies up to roughly 1 billion electron volts per particle. When a massive star exhausts its nuclear fuel, typically after a few million years of hydrogen burning, it undergoes core collapse. The resulting explosion drives a shockwave outward through the surrounding interstellar medium at thousands of kilometers per second. This shockwave persists for thousands of years as it expands and decelerates into the ambient gas, and throughout its existence it functions as a particle accelerator operating on a scale that no human-built device could approach. Charged particles trapped in the magnetic turbulence near the shock front bounce back and forth across the boundary, gaining energy with each crossing. This is called diffusive shock acceleration. Over thousands of years, this mechanism builds particle populations spanning many orders of magnitude in energy, from the barely above thermal to the spectacularly extreme. The process is not perfectly efficient, and not all of the shock's energy goes into cosmic rays, but the fraction that does represents an enormous total energy input into the galactic cosmic ray population, accumulated across the hundreds of supernovae that occur in the Milky Way each century and the billions of years over which they have been occurring. Other source classes contribute to the cosmic ray flux at higher energies. Pulsars, the rapidly rotating neutron stars left behind after certain core collapse supernova, generate intense rotating magnetic fields that can accelerate particles to high energies in their magnetospheres through mechanisms involving the electromagnetic field structure of the rotating dipole. Binary star systems where mass transfers between compact remnants produce shocks and magnetic environments capable of additional particle acceleration. And at the extreme high energy end, the supermassive black holes at the centers of active galaxies generate jets of relativistic plasma that can produce the highest energy cosmic rays observed anywhere, particles so energetic they may have originated in other galaxies entirely and traversed millions of light years of intergalactic space before arriving at the Milky Way. The galactic cosmic ray population in interstellar space is, as Voyager's measurements confirmed, substantial by any standard applicable to the radiation environments of space. It represents a continuous rain of high-energy particles arriving from every direction simultaneously, the accumulated product of violent events spread across the history and the volume of an entire galaxy. Some individual particles have been bouncing through the interstellar medium for millions of years before arriving at any given location. Their original source long since faded, their direction information scrambled by countless deflections in the tangled galactic magnetic field, carrying no record of their origin except the energy imprinted on them at the moment of their acceleration. And every one of these particles was present in full force the moment Voyager 1 crossed the heliopause, in concentrations the spacecraft had never measured in 35 years of heliospheric travel. The heliosphere does not admit this rain freely. It blocks the majority of galactic cosmic rays through a shielding mechanism that is electromagnetic rather than physical, operating through the interaction between incoming charged particles and the magnetic field that the solar wind carries throughout the heliosphere's volume. Galactic cosmic rays are electrically charged. Any electrically charged particle moving through a magnetic field experiences a force perpendicular to both its velocity and the field direction. That force continuously deflects and curves its trajectory. In the complex, turbulent, constantly shifting magnetic environment of the heliosphere, incoming galactic cosmic rays encounter a maze of field lines that deflects them repeatedly in unpredictable directions. Lower energy cosmic rays, which have a smaller momentum and are therefore more susceptible to magnetic deflection, get scattered repeatedly as they attempt to penetrate inward. Their trajectories become randomized. Many are turned back entirely before they reach the inner solar system. Higher energy cosmic rays have greater momentum and resist deflection more effectively. Some punch through the heliosphere's magnetic maze and reach Earth's vicinity, but even these are partially moderated by the journey. The effectiveness of this shielding is not constant. It fluctuates with the solar cycle on an 11-year rhythm. During solar maximum, the sun is most active. The solar wind is stronger and more turbulent. The heliospheric magnetic field is more intense and more disordered, and the heliosphere's cosmic ray shielding reaches its maximum effectiveness. The galactic cosmic ray flux reaching the inner solar system drops measurably during solar maximum compared to solar minimum. Ground-based neutron monitors and space-based particle detectors have tracked this variation continuously for more than 70 years. During solar minimum, the reverse applies. The weaker solar wind produces a less effective magnetic maze. More galactic cosmic rays penetrate inward, and the flux in the inner solar system increases. This 11-year oscillation is one of the most reliably documented phenomena in space physics, a clock whose regularity reflects the sun's own internal magnetic cycle operating on its characteristic timescale. The quantitative impact of the heliosphere's shielding, now measurable with direct comparison thanks to Voyager's interstellar data, is what transforms the heliopause from an interesting physical feature into something that demands attention from everyone who thinks seriously about habitability or space exploration. The heliosphere reduces the galactic cosmic ray flux reaching the inner solar system by approximately 70 to 75% compared to the unshielded interstellar value that Voyager measured. 75%. That is not a marginal adjustment. For lower energy cosmic rays, those below roughly 1 billion electron volts per nucleon, the suppression is dramatically more effective, reducing the flux by factors of 5 to 10 or more. Only the most energetic galactic cosmic rays, those above roughly 10 billion electron volts per nucleon, pass through the heliosphere with relatively little attenuation. This is not a marginal effect, not a 10% adjustment, not a factor of 2 difference. It is the difference, for the lower energy component that is most biologically damaging, between a moderate radiation environment and one that is catastrophically hostile to complex organic chemistry over geological timescales. The heliosphere is not merely interesting, it is the physical basis for the difference between the inner solar system as a potentially habitable environment and the inner solar system as an irradiated zone. Without it, the accumulation of molecular damage over millions of years would substantially alter the chemistry of any biological system. Galactic cosmic rays interact with matter in ways that are qualitatively different from the ultraviolet radiation and X-rays that dominate most discussions of space radiation hazards. Ultraviolet light and lower energy X-rays damage biological tissue by ionizing atoms along a relatively short track through the material, breaking chemical bonds and producing reactive oxygen species that damage nearby molecules. This is the mechanism behind sunburn, radiation sickness from medical or industrial radiation sources, and the long-term carcinogenic effects of chronic low-dose radiation exposure. It is a real hazard, but it is one that matter moderates effectively. A few millimeters of aluminum, or a few centimeters of water, stops most of the solar and cosmic radiation that the heliosphere does not already block. Galactic cosmic rays, particularly the heavy high-energy ions that Voyager measured at full galactic flux beyond the heliopause, operate at a fundamentally different scale. When a high-energy ion nucleus travelling at 90% of the speed of light strikes biological tissue, it does not merely ionize atoms along a gentle track. It shatters atomic nuclei. It produces cascades of secondary particles, neutrons, protons, pions, and heavier nuclear fragments that spray outward from the primary track and damage tissue over a wide cross-sectional volume. A single ion cosmic ray can destroy every cell along its entire path through tissue and damage additional cells in a surrounding cylinder meters across by the secondary particles its passage generates. The damage to DNA is not the isolated single-strand breaks that cellular repair mechanisms handle routinely and efficiently. It is clustered multi-site damage, simultaneous breaks in both strands of the double helix at multiple nearby locations, a form of molecular destruction that overwhelms the repair systems that evolution developed in response to the radiation environment inside the heliosphere and at Earth's surface. These qualitative differences matter because they mean that the biological hazard of the interstellar cosmic ray environment cannot simply be scaled from existing heliospheric radiation data. The character of the radiation changes at the heliopause, not just its intensity. The shielding requirements for any crew on any interstellar transit are not merely more stringent than existing heliospheric shielding. They are in a different category of engineering challenge. Radiation shielding for galactic cosmic rays at full interstellar flux has a deeply uncomfortable physical property that any designer of interstellar spacecraft must confront. For galactic cosmic rays above certain energy thresholds, adding conventional aluminum or steel shielding to a spacecraft hull actually increases the total dose delivered to anything inside the spacecraft. The interaction between incoming high-energy particles and the aluminum nuclei produces cascades of secondary particles that can be more biologically damaging than the original cosmic ray would have been in the absence of the shield. Not less, not the same, more. The shield becomes a particle multiplier rather than a particle absorber. Hydrogenous materials perform substantially better because hydrogen nuclei, which are simply protons, are close in mass to the incoming protons that dominate the cosmic ray flux, and interactions between similar mass particles transfer energy efficiently without producing heavy secondary fragments. Polyethylene, water, and liquid hydrogen have all been proposed as superior shielding materials. Optimized hydrogen-rich shielding can reduce the galactic cosmic ray dose by roughly 30 to 50% compared to an unshielded exposure, meaningful as a safety margin, but still insufficient. A 50% reduction of Voyager's measured interstellar cosmic ray flux would still leave crew members accumulating radiation doses that substantially exceed the career limits imposed by every major space agency. Taken as a whole, the measurements from both spacecraft produce a coherent and unprecedented scientific portrait. But to appreciate what that portrait means, it helps to understand exactly how different the interstellar data was from what models had predicted before either spacecraft crossed the heliopause. The discrepancies were not the dramatic kind that invalidate a theory. They were the subtler kind that reveal a theory's unexamined assumptions. They force a more rigorous accounting of physical complexity. The plasma density in the interstellar medium, as measured by Voyager 2's functioning plasma science instrument, was somewhat higher than several of the most widely cited pre-crossing models had estimated. Estimates range from approximately 0.03 to 0.08 electrons per cubic centimetre, depending on which model you consulted, and Voyager's measurements sat toward the higher end of that range. Higher density means higher inward pressure. Higher inward pressure means a heliopause that forms closer to the Sun than lower density models predicted. Models built on lower density estimates had anticipated a somewhat larger heliopause standoff distance than the approximately 121 to 122 astronomical units Voyager actually found. This modest discrepancy has implications for how accurately existing models can predict heliospheric behaviour under past epochs, when the surrounding interstellar medium was substantially denser. The magnetic field transition was more gradual than most simulations had produced. Theory had generally predicted a relatively sharp rotation in the magnetic field direction at the boundary, a clean pivot that would mark the crossing as clearly as a geographic boundary marker. The actual data showed a transition occurring over days to weeks rather than hours. Not a knife edge, a membrane. A boundary layer of finite physical thickness where the two field systems intermingle rather than simply abutting each other at a geometric surface. This gradual transition suggests the heliopause functions as a somewhat permeable membrane rather than an impenetrable wall, allowing limited exchange of magnetic field topology and possibly some material between the two plasma systems it separates. The cosmic ray flux distribution at the lowest energies showed a steeper increase upon crossing the heliopause than several models had predicted, meaning the heliosphere is even more effective at blocking the lowest energy galactic cosmic rays than the pre-crossing consensus had suggested. Each of these discrepancies is individually modest. None fundamentally overturns the physical picture of the heliosphere and its interaction with the interstellar medium, but collectively they illustrate a principle that the history of science confirms repeatedly. The details matter, and the details revealed by direct measurement tend to be richer and more complex than the details anticipated by remote inference. Voyager did not find the interstellar medium radically different from what theory predicted. It found it precisely different in exactly the ways that matter most. Remote observation constrains possibilities, direct measurement selects the truth. The comparison between the two crossings added a dimension that neither spacecraft could have provided alone. Voyager 1 crossed the heliopause in the northern hemisphere of the heliosphere at 121.7 astronomical units on the upstream side relative to the solar system's motion through the local interstellar medium. Voyager 2 crossed on the southern flank at 119 astronomical units. The 3 astronomical unit difference in crossing distance confirmed the heliosphere's asymmetry. 2 measurements, 2 independent samples, 1 conclusion. The heliopause is not a sphere. It is an asymmetric structure compressed on the side. The solar system is moving toward and extended on the side it is moving away from, exactly as decades of models had predicted, but never directly confirmed. Voyager 1's crossing, as analysed through plasma wave oscillation data, showed a somewhat more gradual magnetic field transition than Voyager 2's crossing, which the functioning PLS measured directly, and found to be relatively sharp in the plasma properties even if not perfectly instantaneous. This difference in transition character between 2 crossings 6 years apart in different directions indicates that the heliopause surface is not uniform. Some sections of it are thinner and more abrupt. Others have thicker boundary layers with more extensive mixing between solar and interstellar material. The heliopause is not a smooth shell, it is irregular. It varies along its own surface in ways that no single crossing could have revealed. Between Voyager 1's crossing in 2012 and Voyager 2's crossing in 2018, the Sun had passed through the peak of solar cycle 24, the weakest solar cycle since the space age began, and was declining towards solar minimum. The heliosphere was contracting slightly as the solar wind weakened. Comparing the conditions at the 2 crossings allowed scientists to observe how the heliopause responds to changing solar wind output on the timescale of years, providing a dynamic portrait that a single crossing at a single moment in the solar cycle could never have captured. The heliosphere breathes with the solar cycle. inflating and deflating on an 11-year rhythm as the sun's magnetic activity waxes and wanes. And both Voyager crossings sampled different phases of that breathing at different locations on the heliopore's surface. Together they defined not a point measurement but the beginning of a time series, a record, one that will grow more valuable as the scientific community mines the data in the decades after the spacecraft goes silent. The implications of Voyager's measurements extend to planetary science in ways that are rarely connected to the mission's narrative in public descriptions, but that follow directly from the data. Consider the situation on Mars. Mars lacks a global magnetic field, having lost it approximately 4 billion years ago when its iron core cooled and solidified. Without a global magnetic field, Mars cannot deflect charged particles the way Earth does. It also has only a thin atmosphere, roughly 1% of Earth's atmospheric pressure at the surface, providing far less material shielding against energetic particles than Earth's atmosphere does. Inside the heliosphere, the heliospheric magnetic field and the solar wind provide some modulation of the galactic cosmic ray flux even at Mars's distance from the Sun, although the modulation is less effective at 1.5 astronomical units than at Earth's distance, because the heliospheric magnetic field strength and turbulence decrease with distance from the Sun. If the heliosphere were compressed significantly, reducing its effectiveness as a cosmic ray moderator, the galactic cosmic ray flux at Mars's surface would increase proportionally. The radiation environment at the Martian surface, already substantially more hostile to surface life than Earth's, because of the absent magnetosphere and thin atmosphere, would become more hostile still. The same logic applies to the icy moons of the outer solar system that represent the best remaining candidates for extraterrestrial life in our neighbourhood. Europa and Ganymede at Jupiter, Enceladus and Titan at Saturn, Miranda and Titania at Uranus, Triton at Neptune. These bodies orbit at distances of 5 to 30 astronomical units from the Sun, deeper in the heliosphere than Mars, but farther from the Sun's moderating influence. At their distances, the galactic cosmic ray flux is already higher than at Earth's orbit by a modest factor, because the heliospheric magnetic modulation weakens with distance. If the heliosphere compressed significantly, the increase in galactic cosmic ray flux at those distances would be more pronounced than the increase at Earth, because the compressed heliosphere would be less effective at shielding the outer regions. For bodies with potential subsurface oceans like Europa and Enceladus, increased cosmic ray bombardment of the overlying ice shells would enhance radiolysis, the chemical decomposition of water molecules by radiation, the ice surface. This would change the chemical composition of the material cycling between the surface and the subsurface ocean, potentially altering the chemical environment of any subsurface habitats. The heliosphere's protection is not uniform across the solar system. It is most effective close to the Sun, where the heliospheric magnetic field is strongest and most turbulent, and progressively less effective at greater distances. But it is a system-wide influence, and Voyager's measurement of the baseline interstellar flux against which the heliosphere's effectiveness is compared allows for the first time a quantitative assessment of how much protection each solar system body currently receives and how that protection would change under different heliospheric conditions. The interstellar medium's interaction with Earth specifically is worth examining separately, because Earth's multiple protective layers create a complex and often misunderstood picture. Earth is shielded by the 3 distinct systems working in series. The heliosphere is first. It filters approximately 75% of incoming galactic cosmic rays before they reach Earth's vicinity. Earth's magnetosphere is second. It deflects a substantial fraction of the charged particles that do reach the inner solar system, particularly those at lower energies, directing them into the Van Allen radiation belts, or causing them to spiral toward the polar regions. Earth's atmosphere is third, with a mass equivalent to approximately 10 meters of water distributed across the planet's entire surface. It absorbs and attenuates most of the particles and secondary radiation that penetrate the magnetosphere. 3 layers, 3 independent systems, each doing its part. What reaches the ground after passing through all 3 is a fraction of the original galactic cosmic ray flux, attenuated by factors that differ dramatically by particle energy and by geographic location. Now consider what happens if the first layer weakens. If the heliosphere's attenuation factor were halved by compression from the current 75% to roughly 40%, the cosmic ray flux at every point in the chain downstream would increase accordingly. The magnetosphere and atmosphere would still perform their functions at the same fractional efficiency, but the baseline entering the system would be higher. The output at Earth's surface would therefore be higher. At sea level, the increase would be modest, perhaps a 20 to 30% enhancement over the current background, because the atmosphere provides effective shielding for most galactic cosmic rays regardless of the upstream flux. But at aircraft altitudes where the atmospheric shielding is substantially reduced, the increase would be more significant. At the surface of the Moon, which has neither magnetic field nor atmosphere, the enhancement would be directly proportional to the change in heliospheric filtering. At the surface of Mars or in the orbital environment of the outer solar system, the changes would be substantial enough to matter for any biological system operating there. The heliosphere is the first and most important line of defense. It is not a backup, it is not supplementary, it is the upstream filter that sets the baseline from which all other protective systems work, and its effectiveness characterized for the first time by direct comparison of in situ data from both sides of the boundary is now a number rather than an estimate. The 75% shielding that the heliosphere provides against the galactic cosmic ray flux is not a fixed constant built into the geometry of the solar system. It is a dynamic equilibrium that has fluctuated throughout Earth's history, and will continue to fluctuate on timescales both shorter and longer than any human civilization. On the shortest timescales, the 11-year solar cycle imposes an oscillation in cosmic ray intensity that instruments have tracked continuously for 7 decades, and that geological proxies, including the production rates of cosmogenic isotopes like beryllium-10 in ice cores and carbon-14 in tree rings, have reconstructed over much longer intervals. On longer timescales, the Sun's magnetic activity level varies with cycles lasting decades to centuries, producing periods of enhanced solar output called grand solar maxima, and periods of reduced output called grand solar minima, during which the heliosphere's shielding effectiveness changes accordingly. But these variations, while real and measurable, are modest compared to the variability that operates on geological timescales. The heliosphere has not always been the size it is today. It responds to the external conditions it encounters, and those conditions change as the solar system moves through the galaxy. Right now, the solar system is traversing a region of the local interstellar medium called the local interstellar cloud, a warm and moderately dense patch of partially ionized gas roughly 30 light-years across. The density of this cloud, approximately 0.1 to 0.3 particles per cubic centimeter, and its temperature, approximately 6,000 to 8,000 Kelvin, determine the inward pressure it exerts on the heliosphere. Those are the conditions Voyager measured just outside the heliopause, and they define where the heliopause currently forms. But the local interstellar cloud is not the only structure in the galactic neighborhood. The solar system is moving through it at roughly 26 kilometers per second, and will exit into a different interstellar environment within the next few thousand to tens of thousands of years. Some models suggest the solar system is approaching the edge of the local interstellar cloud, and may enter a region of lower density material in the relatively near astronomical future, which would allow the heliosphere to expand outward as the external pressure decreases. Other models suggest the possibility of eventually encountering denser regions of the local interstellar medium, which would compress the heliosphere inward. The galactic environment is not uniform. It is patchy, clumpy, and variable on spatial scales ranging from astronomical units to hundreds of light years, and as the solar system orbits the galactic center at roughly 230 kilometers per second, it passes through these patches on timescales that range from thousands to millions of years. Scientists have found evidence that this has happened before, in forms still detectable tens of millions of years later in the geological and ice core record. Studies of deep-sea ferromanganese crusts and Antarctic ice cores have identified anomalous concentrations of the radioactive isotope iron Nan-60, a nuclide produced almost exclusively in supernova explosions and dispersed through the surrounding interstellar medium by the expanding debris field. Elevated iron-60 concentrations have been identified in geological layers corresponding to epochs approximately 2 to 3 million years ago, and again around 6 to 8 million years ago. These deposits indicate that the solar system passed through regions of enhanced interstellar material density during those periods, likely the debris fields of relatively nearby supernova that temporarily increased the density and changed the character of the local interstellar medium surrounding our heliosphere. When the external medium is denser, the inward pressure on the heliopause increases. The heliopause is pushed inward. The heliosphere shrinks. The termination shock moves closer to the Sun. The heliosheath thins, and the magnetic barrier that deflects lower energy galactic cosmic rays becomes less effective because it covers a smaller volume and it encounters the full interstellar flux at closer range to the inner solar system. Estimates suggest that during episodes of moderate heliospheric compression, the heliopause could have been pushed inward from its current distance of roughly 122 astronomical units to perhaps 60 to 80 astronomical units, roughly halving the heliosphere's linear dimensions and substantially reducing its shielding effectiveness. The outer planets would remain inside the heliosphere even under moderate compression. But the cosmic ray flux reaching the inner solar system, including the surface of Earth, would increase. The heliosphere is not permanent, not fixed, not guaranteed to remain the size it is today. It is a conditional shield whose effectiveness depends entirely on what it is currently pressing against. A 2024 study published in the journal Nature Astronomy examined a more extreme scenario than moderate compression. Researchers modelled what would happen if the solar system encountered a cold, dense interstellar cloud with particle densities on the order of 1,000 to 3,000 particles per cubic centimetre, far exceeding the approximately 0.1 to 0.3 particle per cubic centimetre of the current local medium. Under those conditions, the models indicated that the heliosphere could be compressed so dramatically that the heliopause would be pushed inside Earth's orbital distance. Our planet would be directly exposed to the full galactic cosmic ray flux without any heliospheric attenuation, and it would also be directly exposed to the interstellar plasma and its magnetic field. Conditions so different from the present solar environment that the consequences for planetary atmospheric chemistry, surface radiation, and potentially climate would be substantial. The researchers proposed that an encounter of roughly this severity may have occurred approximately 2 million years ago, correlating with geological evidence showing elevated production of cosmogenic nuclides from that period in Antarctic ice cores. The timing overlaps with the onset of a sequence of glaciation events in Earth's recent geological history, the ice ages that have recurred every 100,000 years or so since approximately 2.5 million years ago. Whether the heliospheric compression contributed causally to the initiation of those glaciation cycles is not established and remains actively debated. The mechanism is physically plausible. Increased cosmic ray flux reaching Earth's atmosphere would enhance the rate of ion-induced cloud nucleation in the upper troposphere. More cloud nucleation means more low-level cloud cover. More cloud cover changes the planetary albedo. A changed albedo influences global mean temperature. Changes in the composition of the upper atmosphere caused by the influx of interstellar neutral gas could modify the chemistry of species that participate in the greenhouse effect. These are measurable physical mechanisms with potentially significant climate implications. Whether the magnitude and timing align with the geological record is a question that requires more refined modelling and better constrained geological data. But the underlying physics is sound. The heliosphere's size matters for planetary conditions. Its size has changed. And the driver of those changes, as Voyager's measurements allow us to now see with unprecedented clarity, is the environment that lies just outside the heliopause, pressing inward with a persistence that has been present since long before Earth formed. Consider what this means for life on Earth viewed from the perspective Voyager provides. Every living organism that has ever existed on this planet has done so within the heliosphere. Every evolutionary transition from the first self-replicating molecules to the complex multicellular organisms that now populate every surface environment on Earth occurred within the partial protection the solar wind provides against galactic cosmic rays. This is not a coincidence or an accident of timing. The heliosphere was already approximately its current size when the first identifiable cellular life appeared in the geological record roughly 3.5 billion years ago. Life evolved its biochemistry, its DNA repair mechanisms, its radiation tolerance limits within a radiation environment shaped by the heliosphere's 75% galactic cosmic ray suppression. Remove that suppression, and the baseline radiation environment changes in ways that accumulate over biological timescales. Single-celled organisms exposed to 3 to 4 times the current galactic cosmic ray flux would experience higher rates of DNA damage per unit time, requiring either faster repair mechanisms, greater tolerance for unrepaired damage, or higher rates of extinction of sensitive lineages. Multicellular organisms with complex tissues face the additional challenge that galactic cosmic rays penetrate through skin and bone and organ tissue without the atmospheric shielding that reduces the surface level dose. The radiation dose at depth in tissue, where gonads and bone marrow and other radiosensitive tissues reside, is affected by the cosmic ray flux in ways that are not fully attenuated by the body's own material. These are not hypothetical extrapolations. They are direct applications of the radiation biology established from decades of studying cosmic ray effects in astronaut populations, supplemented by the direct interstellar measurements Voyager provided for the first time. The heliosphere is not a peripheral feature of our solar system. It is the condition that makes the interior of our solar system a fundamentally different radiation environment from galactic space. And it has been performing that function continuously since our star first ignited its solar wind 4.5 billion years ago. There is a metaphor that clarifies what Voyager's measurements reveal about the structure of the galaxy, not as a simplification but as an accurate description of the relevant physics. Every star with a significant stellar wind is a fire. The heliosphere is the light and warmth of the fire, the protected zone where the star's output shapes the local environment and where the dark is held at bay. Interstellar space is the dark. Not the comfortable dark of a clear night far from city lights, which is itself a view from inside a fire. The dark of interstellar space is the dark that exists between fires, cold to within 2.7 degrees of absolute zero, irradiated by galactic cosmic rays arriving from every direction at energies that span 12 orders of magnitude, threaded by a magnetic field shaped by the accumulated violence of supernova explosions distributed across the galaxy's history, filled with a plasma that hums at frequencies characteristic of its own electron density and nowhere else. The dark between fires is not benign. It is the dominant physical environment of the Milky Way, and Voyager 1 crossed from the fire into the dark on August 25, 2012, and has been in the dark ever since. Every day that it transmits, it sends back another data point from the dark. Every number that arrives at the Deep Space Network stations adds to the portrait of an environment that the entire history of human science had been forced to study from the inside, looking outward. through a medium that distorts and modulates and attenuates the signals from the dark before they reach any instrument on any spacecraft or planet inside the fire's boundary. Voyager is in the dark itself. Its instruments are touching the dark directly. And what the dark turns out to contain is not the quiet void that romanticized astronomy tends to picture. It is not serene. It is not empty. It is an active, structured, energetically hostile medium that punishes complexity for entering it. This physical reality, confirmed number by number through Voyager's instruments, carries direct and sobering implications for the most ambitious question humans have ever seriously asked: whether it is possible to travel between the stars. The answer to that question depends not only on the distances involved, which are genuinely staggering, but on the nature of the environment that fills those distances. Voyager has now told us in measured, quantified, peer-reviewed data what that environment contains. The implications are not comfortable, but they are honest. Begin with the radiation problem. Any spacecraft that crosses the heliopause and enters the environment Voyager measured must contend with the full galactic cosmic ray flux from that moment onward, without relief, without variation based on anything our technology can influence, for the entire duration of the transit. At Voyager's measured flux levels, the radiation dose rate in interstellar space substantially exceeds the annual limits imposed by every major space agency on crewed missions within the Heliosphere. Not by a small margin, by a factor that would represent a serious engineering challenge, even for shielding systems far more sophisticated than any currently in use or under active development. The shielding problem is particularly intractable for the heavy, high-energy cosmic ray ions that Voyager documented as part of the full galactic flux. Ion nuclei travelling at 90% of the speed of light carry approximately 900 million electron volts per nucleon, a momentum so large that deflecting them with magnetic fields requires field strengths that, if generated by superconducting coils of practical dimensions, would produce intense fields in the crew's living spaces with their own biological effects on human physiology. The mass and power requirements of a magnetic shielding system capable of deflecting even the lower energy component of the full galactic cosmic ray spectrum would dominate the mass budget of any spacecraft conceived within current engineering parameters. Physical shielding using hydrogenous materials could reduce the dose by 30 to 50%, but reducing 50% of an exposure that substantially exceeds safe limits still leaves crew members in unsafe conditions over mission timescales of decades. The biological consequences of chronic high-dose galactic cosmic ray exposure include elevated lifetime cancer risk, accelerated cardiovascular disease, cataract formation at rates higher than in the heliospheric environment, and growing evidence of central nervous system effects including cognitive degradation associated with heavy ion bombardment of neural tissue. None of these consequences were previously measurable in the full galactic cosmic ray environment, because no human instrument had ever been in that environment long enough to characterize it until Voyager provided the data. The energy problem compounds the radiation problem without resolving it. Inside the heliosphere, spacecraft can use solar panels as a power source out to roughly 5 astronomical units, beyond which the solar flux becomes too weak for practical energy generation. Radioisotope thermoelectric generators extend that range effectively, as both Voyager spacecraft have demonstrated across nearly 50 years of operation. But RTG power output decays continuously as the radioactive fuel depletes, following the half-life of the fuel isotope. Plutonium-238, which has powered both Voyagers throughout their missions, has a half-life of 87.7 years. After one half-life, the power output has dropped by 50%. After 2 half-lives, it has dropped to 25% of the launch value. The Voyagers themselves, launched in 1977, currently produce roughly 45% of their launch power and that fraction declines at approximately 4 watts per year. A transit to the nearest star system, Alpha Centauri at 4.24 light-years, would require more than 70,000 years at Voyager's current velocity of approximately 17 kilometers per second. Over that span, the plutonium-238 fuel would be completely exhausted within a few centuries, leaving the spacecraft without power for the overwhelming majority of the journey. Nuclear fission reactors could provide higher power output over longer periods than RTGs. But even the most optimistic projections for advanced space-rated fission systems face a fundamental constraint. A reactor designed to operate for decades without maintenance, in the interstellar environment Voyager measured, would need to meet reliability standards that exceed those of any system ever built for terrestrial or space applications. The interstellar medium offers no supplementary energy source. There is no sunlight to collect. The particle density is far too low to fuel any ram scoop system at the velocities a spacecraft would be travelling. The magnetic field energy density is negligible as a source for practical extraction. An interstellar spacecraft would carry every unit of energy it would ever use from the moment of departure, with no possibility of resupply, and would need to allocate that finite energy among propulsion, radiation shielding, thermal management, life support, and communication simultaneously for a duration potentially spanning decades. The thermal problem deserves specific attention because it operates independently of the energy problem and reinforces it. Far from any star, any unheated surface in interstellar space radiates its thermal energy into the cosmic microwave background and reaches equilibrium at approximately 2.7 Kelvin, roughly 270 degrees Celsius below zero. At these temperatures, most lubricants used in mechanical systems solidify. Battery electrolytes freeze, certain electronic components cease to function. Structural materials that perform well in the temperature ranges encountered inside the heliosphere become brittle in ways that laboratory tests at cryogenic temperatures cannot fully replicate over the timescales of interstellar transit. Every watt consumed by heating systems is a watt unavailable for propulsion, shielding, and the other demands of a functional spacecraft. The thermal management problem and the power problem are not separate challenges to be solved independently. They compete for the same finite resource, and solving one typically makes the other more severe. And none of these problems is the distance itself, which is the aspect of interstellar travel that typically receives the most attention. Set aside all of these environmental challenges. Assume a propulsion system capable of reaching 10% of the speed of light, a velocity roughly 2,000 times greater than Voyager's current speed and far beyond any propulsion technology that exists or is under serious engineering development for macroscopic spacecraft. A transit to Alpha Centauri at that velocity would last approximately 43 years. During every one of those years, the crew would be immersed in the radiation environment Voyager measured. Full galactic cosmic ray flux, no solar power, temperatures approaching absolute zero without continuous heating, no possibility of rescue or resupply. The interstellar medium is not the void that distance-focused descriptions of the challenge imply. It is an ocean, and crossing an ocean requires more than a fast enough vessel. It requires a vessel capable of surviving the ocean's conditions for the entire duration of the crossing. This perspective reveals something about our galaxy that is rarely stated plainly, but that Voyager's measurements now support with hard data. Every star system in the Milky Way that maintains a meaningful stellar wind inflates its own bubble around itself, its own fire against the dark. These fires vary enormously in size and effectiveness. Massive O and B type stars, the brightest and hottest stars in the galaxy, produce powerful stellar winds that create astrospheres potentially hundreds of astronomical units in radius, substantially larger than the heliosphere. Red dwarf stars constitute roughly 70% of all stars in the Milky Way. Their stellar winds are so feeble that their astrospheres may extend only a fraction of the heliosphere's radius, perhaps barely enough to encompass their habitable zones at all. Some stars in particularly dense regions of the interstellar medium may have astrospheres compressed to very small sizes by the external pressure, providing limited protection even for their innermost planets. The variability of stellar protection across the galaxy is substantial and has direct implications for the habitability of planetary systems in different galactic environments. But regardless of the size of any individual stellar bubble, the space between those bubbles is the same dark, and Voyager has measured what the dark contains. When you add up the total volume occupied by all the stellar astrospheres in the Milky Way, summing the bubbles of all several 100 billion stars, the result is a small fraction of the galaxy's total volume. The overwhelming majority of the Milky Way by volume is the interstellar space, the thin plasma, the galactic magnetic field, the cosmic rays, the cold, the electromagnetic hum that no instrument had ever directly detected until a machine the size of a small car crossed the final boundary of our sun's protection on August 25, 2012, and entered it. The galaxy is not a luminous city of stars. It is a sparse archipelago of fires separated by an ocean that is vast and dark and actively hostile to the complexity that fires make possible. The fires are real. They are numerous by human standards of counting. But the ocean between them is the dominant feature of the galaxy measured by volume, by mass of contained material, by the fraction of any conceivable transit that any spacecraft would spend immersed in it. This physical description of the galaxy connects unexpectedly but directly to the most discussed unsolved question in astrobiology. If the galaxy contains hundreds of billions of potentially habitable planets, and if even a tiny fraction of those develop technological civilizations capable of communication or interstellar travel, where is everyone? The absence of any confirmed evidence for extraterrestrial technological civilization, despite the apparent statistical likelihood of its existence, has troubled scientists and philosophers since the physicist Enrico Fermi first articulated the question informally over lunch at Los Alamos in 1950. The proposed explanations are numerous, spanning the exotic to the mundane, the rarity of intelligent life, the tendency of civilizations to self-destruct before reaching interstellar capability, the possibility that signals exist but have not yet been recognized, the hypothesis that civilizations choose not to communicate. All of these deserve consideration, but Voyager's measurements add a physical constraint to this conversation that belongs in it more prominently than it typically appears. The interstellar medium is not a highway, it is not a corridor, it does not connect civilizations efficiently. It separates them with an environment that punishes any physical system complex enough to carry information or life or technology across it. Every civilization that might exist in the galaxy, regardless of its technological sophistication or its lifespan, sits inside its own stellar bubble protected from the galactic environment by its star's wind. If it attempts to send something physical to the next fire, it must cross the dark. And the dark measured by Voyager presents a set of physics-based challenges that scale not with technological sophistication, but with the fundamental properties of matter and electromagnetic radiation. You cannot negotiate with galactic cosmic rays. You cannot engineer around the inverse square law of radiative cooling. You cannot replenish fuel across light years without a source. Not with more money, not with more time, not with more ingenuity. These are not engineering barriers. They are physics. The silence of the galaxy may not primarily reflect the rarity of technological civilizations or their tendency towards self-destruction. It may reflect the structural reality that the galaxy is a collection of fires, burning in a dark that makes physical transit between them prohibitively costly in ways that scale faster than any plausible civilization's ability to solve them. Light travels across the dark easily, Information encoded in electromagnetic signals propagates freely through the sparse interstellar plasma, attenuated by distance but not fundamentally obstructed by the medium's properties. A civilization could send radio messages, optical pulses, or other electromagnetic signals across the dark at the cost of energy that any technological civilization could afford. But sending a physical object, a probe carrying instruments, or a ship carrying crew requires surviving the medium rather than merely transmitting through it. That is a categorically different challenge. Signals cross the dark. Matter endures it. Those are not the same thing. And it is a challenge that Voyager has now described quantitatively for the first time, in measurements that will remain in the scientific record regardless of any subsequent change in our technological capabilities or theoretical understanding. Every probe humanity has ever launched, every astronaut who has ever left Earth's atmosphere, every scientific instrument that has ever orbited any body in the solar system has done so within the Heliosphere. We have never operated anything outside it. Never. Only the 2 Voyagers have been there. Only they know what it actually contains. The Heliosphere has been the assumed, unquestioned universal context for every human space program that has ever existed. It was always there, reducing the cosmic ray flux, providing the magnetic structure that defines the inner solar system's radiation environment, separating the conditions that permit complex chemistry and biological evolution from the conditions that exist in the galaxy at large. We evolved inside the fire without knowing what the dark beyond it contained. Now we know. Voyager went into the dark, it measured the dark, it counted the particles, it mapped the field direction, it quantified the density, it listened to the hum of the plasma and transmitted everything it found back to the planet that built it. At 160 bits per second, across 15 billion miles of cold and darkened radiation, and the data arrived. Not approximately, not modelled, measured. The numbers are in the record now. They will remain in the record regardless of what happens to the spacecraft that produced them. The portrait of the interstellar medium that emerges from Voyager's measurements is not simply a description of what happens to exist beyond the heliopause at this particular moment in cosmic time. It is a window into the fundamental character of the space between stars. A character that has been stable over timescales that dwarf the history of our species. The galactic cosmic ray population that Voyager measured arriving at full flux beyond the heliopause was not created recently. The particles composing it have been accelerating in supernova remnants and other galactic sources continuously for as long as the Milky Way has contained massive stars capable of going supernova, which is to say for billions of years. The galactic magnetic field that Voyager's magnetometers detected beyond the heliopause has been organised in its current configuration by physical processes operating on timescales of millions of years. The expansion and cooling of supernova remnant shock waves, the slow shearing of the galactic magnetic field by differential galactic rotation, the turbulent stirring of the interstellar medium by the motions of stars and gas clouds through the galactic disk, the interstellar plasma that Voyager 2's plasma science instrument directly sampled has been sitting in the local interstellar cloud, the particular patch of partially ionized gas the solar system is currently traversing, for a period comparable to the age of the cloud itself, which formed from the expanding debris of ancient supernova events. Everything Voyager measured in the first few years after crossing the heliopause represents conditions that would have prevailed in essentially this same form for millions of years before the measurement and will prevail for millions of years after the spacecraft goes silent. The interstellar medium is not a dynamic environment on human timescales. It changes, but slowly, with a geological patience that makes even Earth's slowest geological processes seem hasty by comparison. What Voyager measured is not a snapshot of an unusual moment. It is a portrait of the steady state, the ambient conditions that any object must endure for the entire duration of any conceivable interstellar transit. And those conditions, steady and patient and physically precise, are what the data describes. The darkness between the fires has always been this dark. It will always be this dark, and the fires have always been surrounded by it, pressed upon by it from every direction, sustained by the continuous exhalation of their stars against an interstellar medium that has been pressing inward since before the first star in the local group ignited. The heliosphere holds today. It held yesterday. It held for the entire history of life on Earth. But the dark is not passive. The dark is not waiting for anything in particular. The dark simply is, patient with the patience of something that has never needed to hurry and has never had any reason to relent. The data Voyager returned in the years since the Heliopause crossing represents the first direct measurement of galactic space by a human instrument, and that fact belongs in the context of the entire history of observational astronomy. Every telescope ever built, from Galileo's instrument pointed at Jupiter's moons in 1610 to the James Webb Space Telescope pointed at galaxies 13 billion light-years away in 2022, has been an instrument inside the heliosphere looking out through it at the universe beyond. Every measurement of the interstellar medium made by any instrument in the history of science before August 25, 2012, was made from inside the protective bubble, looking through the distorting lens of the heliosphere's magnetic field and its particle population. The absorption of ultraviolet light by interstellar hydrogen, the scattering of radio signals by free electrons in the interstellar plasma, the polarization of distant starlight by aligned interstellar dust grains, the distribution of galactic cosmic ray energies reconstructed from secondary particles produced in Earth's upper atmosphere. All of these techniques are genuine and powerful methods that have produced an enormously detailed picture of the interstellar medium. But they are all indirect. They all infer conditions at a location where no instrument has been, from measurements taken at a location far from that one, using physical relationships that must be calibrated against assumptions. Voyager removed the assumptions, not all of them. Not for all locations in interstellar space or all epochs in galactic history, but for the local interstellar medium, at this moment, at this position in the solar system's galactic orbit, Voyager replaced inference with measurement. It went to the place, it counted the particles, it measured the fields, it sampled the plasma, it listened to the hum, and it sent the numbers back. That is a category of evidence different in kind from remote observation. It matters in the same way that any in situ measurement matters when it becomes possible for the first time. Not because it always disagrees dramatically with what remote observation suggested, but because it removes the residual uncertainty and replaces it with the confidence that only direct contact with the thing being measured can provide. Voyager 1 and Voyager 2 are going sen, not metaphorically, not gradually in any way that allows for intervention. They are dying in the only way a machine dies when no one can reach it for repairs, by running out of the power required to keep their instruments alive. The radioisotope thermoelectric generators aboard each spacecraft convert the heat of decaying plutonium-238 into electricity through thermoelectric junctions, devices that exploit the temperature difference between the hot plutonium fuel and the cold of space to generate a voltage. At launch in 1977, each spacecraft's 3 RTGs produced approximately 470 watts of electrical power. By the mid-2020s, that output had declined to roughly 200 watts or less, a reduction of more than 50% driven partly by the depletion of the fuel and partly by the degradation of the thermoelectric junctions themselves, which become less efficient at converting thermal energy to electricity as they age. NASA's engineers at JPL have responded to this declining power budget with extraordinary ingenuity, systematically shutting down instruments and heaters as the margin for maintaining all systems simultaneously has narrowed year by year. The cameras were powered down in 1990, 35 years ago, because rotating the scan platform consumed electricity that could no longer be allocated to that function without compromising the science instruments still capable of returning data. Heaters for individual instrument subsystems have been deactivated one by one, exposing electronic components to temperatures they were never designed to survive, and finding in many cases that well-built hardware can endure conditions beyond its design specifications when there is no alternative. Each deactivation buys a few more years of data from the instruments that remain. But even extraordinary ingenuity has limits that thermodynamics enforces without sympathy or exception. Within the next few years, the power will no longer be sufficient to operate any science instrument aboard either spacecraft. The last data transmission from Voyager 1 and then later from Voyager 2 will arrive at one of the Deep Space Network's 70-meter dish antennas, be decoded and processed by systems at JPL, and filed in an archive that will outlast the people who filed it. And after that, there will be no more data. The spacecraft will continue outward, carried by their own momentum through the interstellar medium on trajectories governed only by the laws of Newtonian mechanics and general relativity, and the minuscule gravitational perturbations of distant stars encountered over millennia. But they will transmit nothing. They will measure nothing. They will have become the most distant and most scientifically accomplished artifacts in human history. Inert metal, still racing through the dark, carrying instruments that will never again function, and a record that the dark is slowly erasing. Voyager 1's trajectory will carry it within approximately 1.6 light-years of the red dwarf star, Gliese 445 in the constellation Camelopardalis in roughly 40,000 years. Not close enough to enter that star's astrosphere, not close enough for any surviving instrument to detect the star's properties directly. Simply the nearest any human-made object will come to another stellar system for the foreseeable future of our civilization. The spacecraft will not slow down. It cannot slow down. There is nothing to slow it. There is nothing in the interstellar medium that it will encounter between now and that moment to reduce its velocity, and its own thrusters have long since exhausted their useful life. It will pass through the neighbourhood of Gliese 445 and continue outward, heading deeper into a galaxy that will not notice its passage. The golden record mounted on each spacecraft's exterior deserves specific attention as an artifact of the interstellar environment Voyager measured. Each record is a 12-inch gold-plated copper disc encoded with sounds and images from Earth. Greetings in 55 human languages, music drawn from cultures across the planet, the sounds of surf and rain and wind and thunder and the heartbeat of a healthy human adult. Mathematical diagrams indicating Earth's location relative to 14 pulsars. Binary encoded instructions for decoding the disk's content. Carl Sagan and Andrew, who led the team that assembled the record's contents, intended them to survive for at least 1 billion years, under the conditions they expected to prevail in interstellar space, and the physical medium, gold-plated copper, was chosen for its durability. The gold plating will resist the chemical corrosion that would rapidly degrade most other metals. The copper substrate is mechanically stable under the temperature extremes of deep space. The physical record may indeed survive structurally for billions of years, but the interstellar medium that Voyager documented is not benign to the surface features that encode the record's information. Galactic cosmic ray particles strike the record's exposed exterior continuously at the full flux Voyager measured. Protons and heavier ions at energies spanning from millions to billions of electron volts per nucleon, arriving from every direction simultaneously. Each particle impact creates a microscopic track of radiation damage through the gold plating and into the copper substrate beneath. Over thousands of years, these tracks accumulate. Over millions of years, the accumulated damage begins to alter the surface topography at the microscopic scale of the grooves that encode the audio information. The lateral variations in groove position that carry the music and the voices and the heartbeat of Earth will be gradually smoothed and randomized by the continuous rain of particle impacts until the information they encode is no longer recoverable. The timeline of this degradation depends on the specific energetics of the galactic cosmic ray flux and the material properties of the record surface at the relevant dimensional scales, and it has not been precisely modelled. But the qualitative conclusion is inescapable. The same environment that Voyager was built to measure is slowly destroying the record that Voyager carries. The interstellar medium, which has no knowledge of or interest in the intentions of the small creatures who built those disks and launched them into it, will in time return the surface to a uniform smoothness, and the sounds of Earth will be lost to the dark. This outcome is not a failure. It is physics. The interstellar medium does not respond to the significance of what it encounters. A golden record encoding the accumulated cultural heritage of a technological civilization and a fragment of interplanetary debris travelling on a similar trajectory are, to the galactic cosmic ray flux, identical targets. Both are matter. Both get irradiated. The record represents one of the most beautiful and most presumptuous things humanity has ever done. The assumption that something in the dark would find it and be able to read what it said. Whether that assumption will ever be tested in any way we could know about is a question whose answer depends on the physics of interstellar travel and the distribution of technological civilizations in the galaxy. Both of those quantities remain deeply uncertain, but the environment in which the record will spend the overwhelming majority of its existence is no longer uncertain. Voyager measured it, and the measurement tells us that the record is travelling through a medium that is actively working against the preservation of the information it carries, at a rate set by the galactic cosmic ray flux and the physical properties of gold and copper and the particular form of molecular damage produced by high-energy particle bombardment. The record will travel. It will survive structurally for longer than our Sun has yet existed. But the information it carries will fade before the ship that carries it finds any other fire. The data Voyager returned before it goes silent amounts to the most direct and complete characterization of the local interstellar medium ever assembled. Its summary deserves to be stated plainly, before the implications are allowed to carry all the weight. The particle environment beyond the heliopause is dominated by the galactic cosmic rays arriving from all directions at a flux 2 to 3 times higher than the maximum values inside the heliosphere even during solar minimum conditions. For cosmic rays in the lower energy range below roughly 200 million electron volts per nucleon, the increase is substantially more dramatic, representing the population that the heliosphere most effectively suppresses and that causes the most concentrated DNA damage per particle in biological tissue. The anomalous cosmic ray population, a product of the heliosphere's own internal physics that exists only inside the heliopause, is entirely absent in interstellar space. The magnetic field beyond the heliopause is galactic in origin, slightly stronger than the exhausted solar field in the outer Helios heath, oriented at an angle significantly different from the solar equatorial field, and permeated by turbulent fluctuations on timescales from hours to years that reflect the dynamical activity of the local interstellar medium. The transition between solar and galactic magnetic domains at the heliopause is not a sharp boundary, but a finite transition layer of mixed character, whose thickness and properties vary along the heliopause's surface as the two Voyager crossings demonstrated by finding different transition profiles at their respective crossing points. The plasma in the interstellar medium has a density of approximately 0.05 to 0.1 electrons per cubic centimetre, 25 to 50 times denser than the outer Helios heath plasma. It is warm in terms of particle kinetic energy, at approximately 30,000 to 50,000 Kelvin. It is essentially stationary relative to the spacecraft, and it hums at a characteristic frequency of roughly 2 to 3 kHz, determined by the local electron density. The cosmic microwave background maintains the effective temperature of any unheated surface in interstellar space at approximately 2.7 Kelvin. None of these parameters fully match the predictions of the models that preceded the crossing. The plasma density was somewhat higher than expected. The magnetic transition was more gradual than anticipated. The low-energy cosmic ray flux showed a steeper increase than several widely used models had predicted. The turbulent spectrum of both magnetic and density fluctuations proved richer and more complex than simplified theoretical treatments had assumed. Every one of these discrepancies was individually modest. Collectively, they demonstrated what direct measurement always demonstrates when it finally becomes possible, that remote observation, however sophisticated, constrains possibilities rather than selecting truth, and that truth tends to be more complex and more interesting than the most refined models suggest in advance. Somewhere out there right now, beyond the reach of any warmth our sun has ever produced, a spacecraft the size of a small motorcycle with a rider aboard is drifting silently through an environment it was built to measure. It moves at a velocity that would carry it from the Atlantic coast to the Pacific coast of the United States in slightly less than 8 minutes. And yet in a full year it covers a distance that would require the International Space Station roughly 25,000 years to match. The interstellar plasma hums around it at 2.7 kHz. Galactic cosmic rays arrive at it from every direction at energies spanning from millions to billions of electron volts, particles that began their journeys in supernova explosions that occurred before the first multicellular organism evolved on Earth. The galactic magnetic field threads through it, carrying the accumulated imprint of supernova shock waves and stellar winds and interstellar cloud collisions spanning the entire history of the Milky Way, and the spacecraft, with instruments built from components that were approaching technological obsolescence the year it launched, transmits the numbers back to a planet whose distance in light time now exceeds 45 hours round trip. A command sent from Earth today will not arrive at Voyager until tomorrow afternoon. Any response will not return until the day after that. The numbers come back at 160 bits per second. Every bit is unprecedented. Every count of every cosmic ray particle, every measurement of every field component, every oscillation detected by the plasma wave instrument in the plasma hum that has never been heard before and that no other human instrument is positioned to detect. The data arrives, it is processed, it is stored, and it is honest in the way that only data produced by an instrument immersed in the thing it is measuring can be honest. Not inferred from stellar spectra, not extrapolated from theoretical models, not estimated from the secondary effects of the interstellar medium on objects observed from inside the heliosphere, measured directly from inside the thing itself, from the dark. And when the instruments finally go quiet, when the last watt of power from the decaying plutonium is insufficient to keep the transmitter alive, the spacecraft will continue outward through the dark. It will carry what it has measured in the memory of its systems. It will carry the damage record accumulating in the grooves of its golden disk. It will head toward Gliese 445 and then beyond, into the galaxy, silent and cold and still moving at a speed no human being has ever matched. Never stopping, never arriving. A fire that went out in the dark between fires, where the dark has been patient since before the first star ignited and will be patient long after the last one fades. What Voyager has given us in the end is not merely data, it has given us orientation. Before Voyager crossed the heliopause, humanity had no direct measurement of the environment that fills the overwhelming majority of the galaxy. We had models, and the models were good, built on decades of careful indirect observation and sophisticated theoretical analysis. But a model is not a measurement. A model is a statement about what conditions should be like at a place you have not visited, informed by what you can observe from where you are, constrained by the physics you understand Voyager visited. And the truth it found was more complex, more precisely characterized, and in some ways more demanding than the models had fully prepared us for. The galactic cosmic ray flux is higher than the most optimistic pre-crossing estimates. The boundary is more gradual and more physically interesting than the simple spherical shell of theoretical drawings. The interstellar plasma hums with a voice that no one had anticipated detecting in the form it arrived. Every one of these departures from prior expectation is a gift, because every departure tells us something specific about reality that inference had been unable to nail down. This is what space exploration has always done when it works best. Not confirmed what we expected, replaced expectation with knowledge, and the knowledge Voyager returned, in this case, carries a particular weight. It is knowledge about the context in which our entire civilization exists. We are, all of us, every living thing on this planet, inhabitants of a fire in the dark. The fire is real and warm and has been burning for 4.5 billion years. The dark is real and cold and has been there since before the first star ignited anywhere in the observable universe. Between them is a boundary that Voyager crossed, measured, characterized, and transmitted home. The boundary is not a wall, it is a membrane. The fire is not eternal, it is sustained by a star that will exhaust its fuel in roughly 5 billion years, at which point the heliosphere will dissipate and what was inside it will be exposed for the first time to the conditions that Voyager spent its mission describing. That moment is far enough in the future that it concerns no living organism and no conceivable civilization descended from those alive today. But it is not infinitely far, and the data Voyager returned will still be in the archive when it arrives. A record of what the boundary looked like from the inside, a record of what the dark contained beyond it. Preserved in the scientific literature of a species that will be long gone by the time it is relevant, in a form that only matters if the universe is the kind of place where knowledge outlasts the knowing,